9. Magnetic resistance. Order set. Number 9. Magnetic resistance.
very similar to a classical pendulum. However, in the second stage, we can see that there are some erratic movements that we can observe, mainly in the form of these wave packets that seem to form. So we can see that the amplitude actually decreases and increases and decreases and increases and so on. So this is quite different from what we expect from a classical pendulum. And finally, when most of the kinetic energy has been dissipated, a magnet then simply vibrates above the fixed magnet. Next, I think we also need to consider some geomagnetic forces, because magnet I used on the pendulum is quite light, and so the Earth will exert a magnetic force on it. And I think that maybe the Earth's magnetic field will cause the pendulum to act sort of like a compass. So I did experiments in two directions and found that it did seem to have more deviations to the north and south direction when I swung it east to west. So I'm going to mainly focus my experiments on when the pendulum is swinging north to south. And next, I also calculated the magnetization of my magnet so that I can calculate the magnetic dipole of my magnet in order to include it in my theory. Okay, next, I want to talk about my theory. So first, just considering one magnet, I think we can use Newton's second law to analyze the different forces acting on a magnet, which I think mainly are the magnetic forces, gravity, and friction. And also, since there are two moving magnets and the magnetic field is actually changing, so I think there could actually be some eddy currents generated in the magnet. Okay, so first for the magnetic force, I consider them to be two magnetic dipoles, and so we can calculate the magnetic force like this. As for the eddy current force, we just consider the electric field and the conductivity of the magnet. Finally, for the friction and air resistance, etc., we did an experiment where there was no fixed magnet beneath the pendulum, so that we can consider all the different damping forces like friction, and we fitted damping quotient to our experimental data and found this coefficient. So we can use this equation to solve for our theory. Okay, so this is the result of my simulation, so which we'll discuss later. Next, I'm going to talk about my experiments. So first, I did experiments with only one magnet. And the first parameter is going to be the distance between a magnet. And as you can see, when the magnet was very close to the fixed magnet, the magnet on the string becomes very rapidly damped down, so the motion stops very quickly. And when we increase the distance slightly, we can see that the direction of the pendulum actually does change quite a bit. There are some petal-like trajectories going out from the center where the fixed magnet is at. Finally, and when we further increase the distance, we see that the deviation from the original direction of the pendulum increases, and when we further increase the distance, it continues to increase. And finally, when it is much further away from the fixed magnet, we can see that the fixed magnetic force is no longer the dominant force. And so this pendulum is mainly only affected by geomagnetic force, hence the small deviations, and except for that, it's just like a simple pendulum. So to sum up, when the magnet is too close, we may see some very big damping, so it will stop very quickly. And when we slightly increase the distance, we can see very large changes in the direction of the pendulum. And when we further increase the distance, the changing direction kind of decreases. And when the distance increases very much, like for example, the 40 centimeter experiment class I did, then we see almost no change in direction. However, we can see that there are some differences between my theory and my experiment, mostly in the form of those wave packets I mentioned earlier. So in my theory, the magnet's displacement will just continue to in my experiment, they seem to go up and down with those wave packets. So my theory does not account for these deviations. So I think that I need to expand my theory from 1 dimension to 2 dimensions. So I think we can use magnetic potential energy to simulate this, as it will kind of simplify this. The calculation will be greatly simplified. So we expand it into 2 directions. We consider the resistance from the magnet, and we can write this equation of motion. So we also use Python to numerically model this. And so we can see that our new theory now does actually have those deviations that we did observe in our experiment, which suggests that this theory does fix some of those flaws. And next, I'll talk about the offset distance. So I changed the offset distance, which is the how long the distance the fixed magnet is from the trajectory of the pendulum. So when we further increase the offset distance, I think we can see more pronounced wave packets. And also, there seem to be more of those wave packets. And like the wave packets, I think are formed because the pendulum is changing in direction. This means that the offset is actually causing the pendulum to change in its direction. So I think, as I mentioned earlier, the change in direction is most likely due to there being a slight offset between the fixed magnet and the point of the pendulum where it is resting if there was no magnet. So as I mentioned, if we included this very small deviation in the position in our new theory, it causes the wave packet that we observed earlier, which I think supports my hypothesis. Okay, next, we also discussed the 2 magnets case. Okay, yes, so first, when the magnets are at a very close distance, we can see that it seems to become very quickly damped down and slowed down when it gets close to the magnet, and also it only stops near one of those magnets. When we further increase the distance, the pendulum then will be able to stop in the middle of the 2 magnets as the magnetic force is no longer as strong. And as we mentioned earlier, when we further increase the distance, the change in direction seems to become smaller. And next, I changed the orientation of the 2 magnets to be parallel and normal to the direction the pendulum is moving in. So to observe the differences between them. So this is the parallel one and this is the perpendicular one. So to compare them, we can see that when the magnets are kind of perpendicular to the trajectory, we can see some very big changes in the direction. So I think that is because the magnets on the 2 sides are attracting the pendulum, and so there are some bigger changes in the direction the pendulum is moving in. Also, I think from the above experiments, we can see that the movement of the magnetic pendulum is actually quite unpredictable. So I think I try to calculate the upper of experiment and try to measure if it is actually chaotic. So the upper of experiment measures how much the initial deviation actually expands. So when it is larger than 0, the initial deviation will grow exponentially. So for example, for the experiment, I used 2 magnets. The distance between them was between the pendulum and the middle of the fixed magnet was about 3.5 centimeters. Then I overlaid these 3 trajectories on top of them. And so I think that to measure this experimentally, we need to consider the distance between each of these trajectories over time. So we can see that the distance does actually fluctuate. And since I already took the logarithmic of the distance, it is actually growing at an exponential rate. So after discussing with some teachers and looking for some purposes, we can see that the slope of this is how much it we can arrive at this exponential which we were able to calculate. And so I think that this pendulum may be chaotic under certain circumstances. To sum up, we explain the motion using magnetic potential energy, and we fix the field using it. And we also derive the height in other parameters. So when the stimulus gets denser very quickly, and also changes in direction, which I explained using the offset. And that ended my report.
So first I want to ask a question about the magnet. So do you consider about the how big the magnet is, or how the radius of the magnet?
Yes, I did measure the volume.
Okay,
So for the fixed magnet, the diameter is 2.5 centimeters, and it's like 0.5 centimeters high.
so in your numerical model, you consider this thickness, or I guess what you just use the magnetic dipole to do the simulation?
So in my theory, I multiplied the magnetization. So I don't think I included that in my presentation, but I multiplied the magnetization as I did measure it by the volume to get the dipole moment.
Oh, okay. And the next question is, do you use string to connect the magnet and the suspended point?
Yes, as the problem definition, the magnet needs to be suspended from the string, so that's what I did.
So the magnet will swing.
Yes.
Yes, so will this affect the result or not?
Yes, I think that this will maybe change the direction of the magnetic force.
Okay, and I'm going to turn to page 31.
31.
Okay, so you do only these 4 groups, or there are other groups?
As I mentioned in my comparison, there were I actually did more different parameters, but I picked
some
4 different ones.
Oh, okay. And page 46.
46.
Okay, so the space and attract the magnet suspended from the string. And in this case, how the motion depends on the relevant parameters. So the key point is XY motion and damping. And damping has some child elements. And also the position of the magnet. So in the theory, they discovered that there's 3 stages of motion to resemble the movement and analyze the whole force effect and also the potential energy. And theory expanded from 1 dimension to 2 for the sake of pair with the experiment. And in the experiment part, use Tracker and Python to analyze the model. And they also consider about damping and consider about 1 or 2 magnets position. And in the conclusion, they use magnetic potential energy to analyze the result. So the adventure of their report is they explain the phenomenon clearly and consider geometric force. And the theory includes all parameters and it is easy to understand. And they fix the theory because the data and the theory are different between each other. And there's some suggestion. You could explain more about the damping. And you didn't consider the weight and the strength too much in the presentation. And show more demonstrative videos to let us easy to understand what happened in the experiment. And we will discuss some points. First is the different color or same color you use in your experiment. And what kind of initial condition in your experiment. So I want to talk about the experiment setup. So what is freezer in your setup? Freezer, how to fix the magnet and release it in the same way and don't affect it.
So because like your tweezer is in the same position, so I pinch the magnet with the tweezer and then release it when I start the experiment, and then I track the magnet.
Okay, so you use string and the string always be straight, or sometimes it will not straight always.
I didn't measure that, but sometimes the string does vibrate.
Okay, and let's talk about in your observation. There's 3 states of this motion, right?
Yes.
Okay, and could you talk about what is this states look like and more? Can you talk about what it look like?
So I think that for the first stage, because it just moves back and forth like a normal pendulum, so there's so like it would also like a normal pendulum would just like how much it's moving will also become less.
So this graph only consider about the x direction.
This is only one direction.
One direction. Okay. So in the first stage, the magnet will change direction.
I think that yes, as I mentioned, in the first stage, it's just like a classical pendulum, so it doesn't really change directions.
Okay. So that's about also setup. I want to talk about two magnet setup. So it's around page 54. Okay, so you mentioned mentioned the distance, the edge. You change the edge.
Yes.
And did you consider the distance between the two fixed magnets?
Oh, I didn't change that.
Didn't change that.
Yes.
Okay, and the two magnetic fixed magnetic is the same. Is same color.
You mean they are so they both have the same side facing up, so that both magnets will attract the magnets on the string, as the problem statement says.
Okay. And okay, let's talk about so let's talk about theory. And I think it's very beginning and force analyzing. So you have one slide that shows the forces, magnetic force plus the gravity force plus here. What is the AT force compared to this magnet?
So I think that because there are two changing magnetic fields. So I think that because there are these changing fields, their current might be generated in them. But yes, I later kind of wrote some code and calculated it, and I think it is very small.
So it doesn't affect the result much.
Yes.
Okay. And what about air resistance?
So yes.
So did it affect the result much?
Yes. So as I mentioned, I did an experiment where there was no magnets below. So I just swung it without the magnets below, and so it will naturally decrease like the amplitude. So I fitted that to this damping equation, and we can get the speed in the. So it accounts for like friction and air resistance.
Okay. And let's talk about the result of the experiment. And also turn to page 31. I talked about. Okay, so you say you have used another system to do the experiment?
Yes.
Okay, so what is the bounding distance? Not bounding. What is the distance that the motion of the third paragraph will change to the fourth paragraph? Because the fourth paragraph, you can see that no more this direction.
Okay, but maybe I think there's maybe really no fine boundary. So I think that maybe this will just continue to decrease slowly when we increase the distance. But I didn't. So I just compared a few distances, and I didn't find the boundaries.
Okay. And let's talk about page 69. Okay, so you can see the dots. At the beginning, it's lower than the line, right?
Yes.
And then it's higher and it's lower and it's higher. Do you have some the sequel change?
I think because it's experiment, so maybe it will be slightly different from my theory, but I think that is close enough.
Okay. And can you explain the typo? What is the typo?
You mean this one?
Where the like okay. What is that?
Okay, so as I mentioned, I use this it's basically to calculate how if this may be chaotic or not. So we can actually write so as you can see, there's a natural log equation. So when this is bigger than 0, it is it will grow exponentially because there will be e to the power of this exponent. So it will grow very quickly.
Okay, and look at the
think it's kind of different. There are some differences in distance and such.
Okay, and okay, so let's talk about or page. Is your experience? How do you think your experience has some error or not?
Definitely, I think.
What is a more error?
What do you mean?
Like, sorry, I have to organize my words. Okay, so to fix your theory to match the result, and can you tell me when you fixed?
You mean this one?
That is like one magnet or two magnets.
We're talking about this one? Yes, here. Okay, so I kind of because my original theory just assumed it was a straight on the same straight line as the magnet, and so if they were directly above the magnet, then it will be the same on all sides, and so the direction will not change. So it will just be a straight line when we plot the x, y directions. But so we fix this to account for two directions, which are the x and y directions. And so for this graph, we kind of we made a small offset in the distance of the fixed magnet, which we think may be in our experiments because the measurements are not precise enough, and the offsets were kind of like maybe 0.1 or 0.01 centimeters, and the direction of the pendulum will still change.
And look at this picture. I think it's interesting because this part is don't have the trajectory, like the magnet don't get to this part. And you, what's your guess?
Okay, so I think that it depends on maybe the slice of, like the slice distance it is from where it is directly under the pendulum. So when it does that, I think it's causing it. I think it's causing the pendulum to like maybe turn in this direction. So maybe it will turn in that direction.
Okay. And what your result and the period of each piece like that will change or not? Because it's damping, so it goes down, but the period didn't change.
I did not measure the period.
And okay, so talk about all my question.
So the point is the summary.
The tweezer effect system, they design a tweezer and release it, but it not affect the system very much. And our stage looks like the one the polar is they set a polar that the magnet track each other, and then they in the two magnet part they fix the R of the distance between two fixed magnetic and change the change the height of the magnet. And okay, I think, and also they describe what the state change and looks like. And
Okay, hands up. The review.
Okay, I want to ask the reporter and the opponent, how did you define the chaos? Did you use the real situation? Because I see you only use the macro.
What do you mean?
Can you use the real situation to define your chaos?
Yes, I think we have to use some experiments to like calculate it.
But I think because I only
as I did my experiment, we kind of compared the same experiments and their kind of their XY movement.
Okay, thank you. How do you define chaos?
Like how?
Yes.
Like in initial condition, like the position the magnet goes in is different, but so the trajectory of the final result
Okay,
is
thank you. And what is the important independent variable to affect the motion of the moving magnet?
I think that it's going to be the strength of the magnets below, and also the distance, because it will affect the magnetic force. And also how they are laid, like where the magnets are below the pendulum. So when they are at different positions, maybe it will cause the pendulum to swing in.
And so you use a different position or the distance?
Yes, I think it's mainly the distance.
Okay, thank you. How many?
I think the distance and the magnetic mean and how thick and the radius all change.
Okay, thank you. And what is the main factor to let the moving magnet rotate around the fixed magnet?
I think it's because the fixed magnet is not directly below the pendulum. Yes, we try to control it to be exactly below, but our hypothesis is that maybe there are some very small errors.
Okay, thank you. And what is the main factor to let the moving magnet rotate around the fixed magnet?
I think the initial speed, the velocity, and the force between the magnet.
Okay, thank you. And the carbon mentioned the magnetic assist, and what do you think assist is assisting?
So I think it is assisting the magnet in slowing down, because when it
Assist, like velocity or the motion?
yeah, you can also say a lot because it speeds up.
Okay,
Okay, hands up.
indicate the error in the experiment process and a constructive suggestion about the experiment. But I think he should talk about the data and the trajectory change. And in the key discussion, I think the opponent asked the reporter the error that affect the result, and the reporter said the error resistance and the friction may affect the result, and I agree with the report, but the geometrics will also affect the experimental result because I think during the report I know that he used the parallel and the vertical to do the independent variable. So I think in the vertical he needs to consider the geometry. And our question is how did you define your chaos in the real situation? And reporter only used the afternoon to calculate it, and the opponent said the initial condition or the trajectory can define it. And I think the initial condition is highly sensitive, and the start position is unpredictable, can define the chaos. And which independent variable affect the result of the motion of magnet, the clock. And the reporter said it's the fixed magnet and the moving magnet distance. And the opponent said it's the moving magnet release position. And I think it's the number of a fixed magnet because when the number of fixed magnet increase, the magnetic force will decrease. And I asked them, the problem mentioned the magnetic assist, and what do you think assist is assisting? And the reporter said it is a velocity, and the opponent didn't answer me, and I think it is assist the moving magnet's motion and the velocity. And in the missing point, I think the chaos definition in the real situation is a good question to talk about it, because in the real situation, you need to compare the trajectory and the velocity and the x and y. Thank you.
So first, for my concluding remarks in my report, I managed to find out the differences between the three stages of the motion of the pendulum, as I did mention in my report. So first we have a motion, and then we have some strange motions in the form of the wave packets we also talked about, and also it vibrates above the fixed magnet when it starts moving. And also we explained how the magnet seems to change its moving direction because of the offset. And also we changed some parameters in our experiment, such as the number of magnets, 1 and 2 magnets, the different types of the magnet, or the distance between the magnets, and we also changed the offset distance. And so we also did some theory fixes to fix our theory to 2 dimensions. And we also did consider geomagnetic forces. And since the geomagnetism will affect the end results of our experiment, as I mentioned, I did my experiments in the north and the south direction to prevent deviations caused by the Earth's magnetic field. And also, I measured the width and the height of the magnet, and so I calculated the volume of the magnet, and I also considered the strength of the magnet. And also, I have a controllable setup with the tweezer to control the initial position. And as for the release force, because the magnet is released by a tweezer, it does not have release force. Instead, the gravity just pulls it down. And finally, the opponent thinks that I should find the boundary for the different kinds of motions, and maybe I will do that in the future, and that's my concluding remark.
So, questions from the group? So, maybe first one. So, do you consider change the force?
So yeah, I think that I consider the distance between the magnets, so they change with the distance.
And what do you expect will change the magnetic force? The critical distance, how will it change?
I think that when we increase the force, like when the distance is too small, it will stop very quickly. So when we increase the force, maybe the magnetic force, maybe the distance will increase.
The relation will be linear or relation is the magnetic force resistance will be linear or the other relation.
Can you say that?
When you change the magnetic force and the distance, it's changing to be linear or the other.
I think it's maybe cubic.
Very good.
And
Same
so,
question.
can you say that again?
We change the magnetic force and we observe the equal distance, what would be the relation?
To talk about the force depends on the location distance. Or
So we observe the different frequency distance for the behavior. And we change the magnetic force, what would be changed?
I think that we change the magnetic force, if the force increase, but the original projection is like the shape of 8, and the 8 will be bigger. That's the change. And also, if we change one magnetic force and another don't change, and the shape will be more chaos.
I think it is non-linear. So if we change the distance and the magnetic force change, I think the change is non-linear. So maybe the change is not depend.
I think the relationship between the distance and the force depends on what model you consider. The magnetic pole, the point dipole, and the loop pole is different. Depends on what model you choose.
Yeah, thank you very much for the presentation. And I'd like to see the slides on the 7.
7.
You mentioned about 3 stages, and you also show the videos about the motion of the pendulum. Okay. I mean, from your intuitively, how do you think this motion will happen? I'd like to start from the reviewer. How do you think how this happen from this presentation? You mentioned there are 3 stages, right? They also show you the video. Okay. Intuitively, how do you think this motion will happen?
Is motion, is charge motion or?
I mean, this chart, just this chart. You mentioned 3 stages, right?
Yes.
Intuitively, how do you think? You also watch the video, right?
Yes.
And why this happened?
I think at first when he released the magnetic will affected by the release force, so it will like the magnet, and at the same time it will affected by the magnetic force, and when the magnetic force is similar than the jet force, and it will have a vibration over the time.
Okay, thank you. How about opponent?
I think
Follow this presentation.
I think in the beginning the velocity is bigger, and so the kinetic energy and the magnetic potential energy and so
Okay, thank you very much. How about you?
And I think it's because like the direction is changing. So this is only one direction, so you can see it increase and decrease. Thank you.
Okay, thank you very much.
Can I give this a short comment? Since this is the last meeting, we don't have much time. I was suggesting when we discuss the question like this, it's a more complicated pendulum motion. So we should start from simple pendulum. It's like a simple harmonic motion, right? A simple harmonic motion is one-dimensional. And it's linear, we call it linear equation, differential linear equation. It means that f equals minus ax, something like that. And your motion is two-dimensional. That means the force is not like that simple. It depends on maybe x and y or theta and phi. So you should tell us where is the restoring force. We call that restoring force for the simple harmonic motion. And compare that form. So lead us to understand this kind of motion compared to simple pendulum. What is the restoring force? It must be two-dimensional, more complicated. Magnetic force is very complicated, especially its dipole interaction. And you talk a lot about chaos, and for a lot of the fight, chaos again is not a linear equation. That's high-order term. So the pattern may change, depends on the initial condition. Usually there are 2 or 3 patterns that may change. It becomes very complicated. So I don't suggest we should talk much about chaotic motion. We don't, it's not needed. Yeah. Just briefly we get an idea, but focus on the simple physics associated with it, like simple pure pendulum compared to your pendulum. What's the difference? What's the restoring force? Why is it two-dimensional and so on?
Okay. So let's do the version. Start with the recorder. So 7, 8, 6, 7, 8. Then the opponent. 6, 7, 6, 6, 7. And the reviewer. 6, 7, 6, 6, 7.